Yes, thank you very much. This talk today is about very recent work with Nikhil and Ola, and it's about a scheduling problem that I personally have been banging my head against the wall for a few years. So I'm really excited that we could finally make some progress on it. And don't worry, I know it's close to lunch, so this will not be an overly complicated talk, because if you have the right hammer for this problem, then it actually turns out to have a very clean solution. And the right hammer, it comes from discrepancy, more precisely what I call the prefix Beck-Fiala setting. And how does this fit into this workshop? I would say this prefix Beck-Fiala setting, it's a bit of a discrepancy problem with a kind of parameterized flavor to it. And you've also seen in the previous talks that these kind of discrepancy bounds, like for example in the Steinitz setting, they are very relevant, for example, to integer programming. So I hope you will also get something out of this talk. Okay. So let me start by introducing the problem that we have. So we have three machines, or we have an arbitrary number of machines. In this example, 3, and we want to schedule jobs on them. And here I've already put the jobs on some positions, but really your task is to decide where to place these jobs. So each of these jobs, it has some given processing time, which depends on which machine you run it on. So, for example, if I run it on the first machine, it's P1J. If I was to run it somewhere on the second machine, it might have a completely different processing time. So that's what we call the unrelated setting, in contrast to Klaus' talk earlier, where the jobs have like the same running time everywhere. Here, they have different running times, which make the problem much harder. Another part which makes the problem much harder is that each job has a release time, and you are not allowed to schedule this job before it's released. Now, if you have such a schedule and you know the release time, then you can define what is called the flow time of a job, which is the time from when it's released until it's completed. Right? So, and that's a natural quality of service to try to minimize these flow times, so like every job should be finished as soon as possible after it's released. But these flow time kind of problems, they tend to be like terribly difficult. Like there are a couple of variations related to flow time which are like widely open, and progress, well, on some of these problems, progress has been made only in the last couple of years. So this is a really nice field which is still very active, I would say. And in this talk, I want to concentrate on minimizing the maximum flow time among our jobs. So every job should be finished some fixed time after it's released. And we want to minimize this maximum flow time. And if you haven't seen this problem yet, maybe what you know is a famous special case of this, which is just all the jobs are released at time 0, which means, of course, I put the jobs always as far to the left as possible, and my maximum flow time in this case is just equal to the maximum load among all machines. So like the classic makesan minimization on unrelated parallel machines. And well, at least if you only care about constants, we know a very good algorithm for this problem for a long time, which is due to Lenstra-Shmoys-Tardos, and it's a beautiful LP rounding algorithm, and it will be instructive to explain kind of just like a very superficial a roadmap of this algorithm. So we set up an LP relaxation of the problem, and you can see that like the naive LP relaxation, it just has one constraint for every machine, which says the load should be at most something. And that turns out to be like very, very few constraints. So that's good for LP kind of arguments, because if we have few constraints, we have a sparse LP solution with simple non-zero variable patterns, and we managed to exploit this and round this sparse solution to a solution which has an additional load of another opt on each machine. So you get in total 2 times opt load on each machine, which is very nice, gives you this 2 approximation. So very happy about this, why does this not work in the more general case where we have different release times? So obviously it's not enough to just bound the load on each machine, right? It kind of matters how the jobs are released. And the right way to look at it here is that we need to bound the load on each interval of release times. So let's look at one particular machine I, and let's look at all the jobs that are assigned to I. And we look at one interval T1 to T2 and all jobs that are released between T1 and T2. And it turns out that we definitely need to have some bound on the load here, which is the length of the interval plus the maximum flow time, which we want to have. Because this is simple to see. Suppose we have the interval T1 to T2, all jobs are released between these two. So they cannot start before T1, they cannot finish after T2 plus F max. So if, like in this example, the load here would be larger than this T2 minus T1 plus F max, then obviously one of the jobs would have a flow time greater than F max. So these kind of constraints for all the intervals, they are certainly necessary, and it turns out that you do some standard arguments that these constraints are also sufficient. So the right way to look at this max flow time is that we have similar to makespan, but we need the constraints on each interval. And before we had one constraint per machine, but now we have like a ton of constraints for each machine, which increases the number of constraints very much, which is very bad for our LP rounding strategy. Banaszczyk and Kulkarni still managed to get something non-trivial using LP rounding or linear algebraic techniques, and this is also the state of the art right now. Well, what do you notice is the LP solution is not anymore sparse, and it turns out that they managed to increase the optimum by some constant factor, but they can only round half of the variables. So before we were able to round all the variables, now only half at the cost of constant loss. So you repeat this log n times and you get an integral solution, but you have this annoying factor of log n, which is not clear at all whether you need it, because from the lower bound side, we don't know if the problems are, this is more difficult than the simpler problem or not. So I want to avoid this log n factor, or at least get something better, right? So here, of course, this log n is very inherent in this kind of argument. It's not clear at all how to remove it. But in this talk, I will improve on it. And, well, in order to get that, we want to look at a completely different field and kind of borrow techniques from there. Okay, so let me introduce a little bit in discrepancy, which also was mentioned in earlier talks. So in, like the classical discrepancy setting, we are given some elements, these cycles, and we are given a family of sets over these elements. And what we have to do is we have to color the elements in two colors, say red and blue, so that every set has kind of balanced number of red and blue elements, and we want to find out how balanced can we be. And for example, in this coloring, like the worst of the sets is this set up here, which has 3 red and 1 blue, and so the total discrepancy of this coloring in this case would be 2, because it's the worst case over all the sets. So that's kind of the discrepancy setting, and usually you're not so much concerned about approximation algorithms, but you want to show the existence of coloring with a certain discrepancy, given maybe some restrictions on how the sets look like. And one of the classical results in discrepancy is if every element appears in only k many sets, then the discrepancy, well, it depends only on this k. It doesn't depend on the number of elements or the number of sets. If every element just appears in, say, constant number of sets, then we have a constant discrepancy. We can even take this function as a linear in k, which is the proof by Beck-Fiala, and that's a huge open question if you can do something better, ideally a square root k. But how does this kind of proof look? And again, I will give a very superficial overview. So if you look at the p-relaxation of discrepancy, where you can color like half red, half blue, of course this is feasible for discrepancy 0. And now if you look at sets that are smaller than f of k, you can just throw them away because they cannot have a large discrepancy. And a simple counting argument now gives that the remaining sets, there are just a few remaining sets, because every element appears in a few sets, and every set is large. There cannot be too many large sets. So again, we do a linear algebraic proof. We have a system with few constraints. We get a very nice sparse solution, and we can round it very well, getting a discrepancy bound only depending on k, which is very nice. And this should remind you of the earlier proof that we did in the scheduling problem. This is very similar, and of course this is not coincidence. This proof is closely related to the other proof. But how would like extension of this discrepancy to something more closely to the flow time setting with the different release times look like? And for that we look at an extension of the classical discrepancy, the classical discrepancy setting. Now the elements are labeled 1 to n, and you again want to color the elements, but not only do you want to have a good coloring with respect to these sets, but also if I take a prefix of the elements, so for example elements 1 to 5, then I want that the instance restricted to these elements still has a good discrepancy. So for example, here the set had a discrepancy of 3 minus 1, so 2, and now it has a discrepancy of 3. So the question is, find a coloring that is good with respect to the worst case prefix of the elements. And of course you can look again at the Beck-Fiala setting, where every element appears only in k sets. So how does this linear algebraic argument extend to this case? Well, now you again are feasible with discrepancy 0, but you now have a ton of constraints for each set. Before I just had one constraint which kind of said the set should have a discrepancy 0. Now I need to have a constraint for every prefix and every set. So every set now has potentially n many constraints. So the LP solution is not very sparse anymore. I can still, with a few tricks, round half of the elements by increasing the discrepancy by f of k. And of course, I have to repeat this to get like a full coloring, which gives me a bound of f of k times log n. Again, this log n factor is something that I really don't like here. So in this setting, it seems like, again, this is very inherent. And the message here is that we have these two seemingly different problems, and we hit the same wall with them, the same wall of log n. But this is, of course, not the end of the story of this talk, because it turns out in discrepancy we have this brilliant hammer. And we have this tool by Banaszczyk. And, well, he proved this amazing result, which, among other things, that implies that the discrepancy for all prefixes in this Beck-Fiala setting is only f of k square root log n. So, like, of course, this is not the f of k that we would ideally want to have, but at least it breaks with this very natural barrier of log n. So I can't say too much about this technique because it's also not so easy. It's from convex geometry, and it's maybe even more famous because it also gives the best bound towards the Komolosh conjecture that we have at the moment. Very amazing. Maybe one comment, where does this log n come from? So if you look at the hypercube centered at 0, the length of the sides is square root log n, or order of square root log n. This is kind of the order from where the Gaussian measure of this object, it goes from very, very low to very, very high. Right? If you take this constant low, then you have a tiny Gaussian measure. If you take this constant high, you have a huge Gaussian measure, and this is inherent to his proof, and it's also completely unclear how you would avoid this square root log n. So I mean, this is. But anyway, it's a nice improvement over the easy linear algebraic proof in this setting. And well, of course, our roadmap now is to take these better guarantees that we get through this tool and apply them to scheduling to also get the same here. But what will also happen is that by the kind of reduction that we do to implement this discrepancy in scheduling, we also motivate new problems in discrepancy, which might be interesting for discrepancy people to study. And towards this, let me just quickly rephrase Banaszczyk's theorem. You can view it also as coloring 0, 1 vectors. So you have 0, 1 vectors for each element, and each row it kind of corresponds to one set. Now the vector is just the whether this element appears in the set. So discrepancy is really choosing signs -1 or 1 for each of these vectors, such that if you sum up the signed vectors, you get a bounded max norm, because you want to be good in every set. This corresponds to the infinity norm of this signed sum. And well, in the Beck-Fiala setting, we have like bounds on the number of ones, the number of sets an element appears in. So this corresponds to a bounded L1 norm. And Banaszczyk gives us that for every prefix, for every L smaller than n, this prefix sum is bounded by f of k times square root log n. Now, Banaszczyk doesn't really care if it's 0, 1, or if you have arbitrary vectors, as long as the norm is bounded. And so we might as well take arbitrary vectors. And In addition, you might assume you might want to have bounds not only on prefixes but on any interval. So a sum starting at h ending in L, and this is equivalent up to constants, because any interval you can view it as like the difference of two prefixes, right? You take the end, the prefix that ends at the same position, you subtract the prefix that starts that ends at the start, you subtract them. If both prefixes have a bounded infinity norm, then also this interval has a bounded infinity norm, so we get it kind of for free. And finally, this f of k is really O of k in this setting, which is also the only thing that makes sense, because you can always, like in this setting with arbitrary vectors, you can always scale them down and up. So it really only makes sense to have a linear dependence on k. So now I have 5 minutes to explain how we apply that, and I think I managed to. So let's go back to the scheduling problem, and like an easier starting point might be to round half-integral solutions. So every job, half of it might be assigned to one machine, the other half might be assigned to the other machine. So these two halves are equal, but like maybe the processing time is different, so that's why this is longer than this, for example. The color shows you the identity of the jobs. Okay, so like if we want to round this kind of half-integral solution, there are like really two natural ways. We could increase on one machine, like adding the other half of the jobs, which increases by 1/2 times P1j and decreases on the other machine by 1/2 P2j. Or we do the opposite. We decrease on the first machine by 1/2 times P1j and increase on the other machine by 1/2 P2j. Okay, so if you look at how the loads change on our machines, represented by a vector which has one component for each machine, the two options that we have correspond to either taking this vector positive or taking like the negation of it. Like this is how the loads would change if I round it this way or the other way. So maybe let's just recap what we need for the flow time. We needed for every interval of release time, we needed some bound on the load, right? So this half-integral solution, it already has like a good flow time, we assume, and now we just want to round it without increasing the loads on any interval too much. So what we simply do is we construct this vector for every job, and we use Banaszczyk. We sort them by release times. So that means Banaszczyk will give us a bound on the infinity norm of the signed sums on every interval, which kind of corresponds to the change in the loads on every interval. And Banaszczyk, it tells us we get a bound of, well, the maximum L1 norm, which, so we just have two non-zero entries. One is 1/2 P1j minus 1/2 P2j, so we can bound this by the maximum over all Pij. Right, so, and we lose this factor of square root log n. And finally, if you do some standard pre-processing, you can make sure that this maximum Pij is never greater than the optimum max flow time, because kind of if it was greater, you make sure that this job is never assigned to that machine where it's greater. So this gives us a factor square root log n. So if we have a half-integral solution, we can turn it to an integral solution, increasing the max flow time by square root log n. And now, how do we deal with arbitrary solutions? So, like if we solve an LP, we don't get a half-integral solution. Unfortunately, we get a very fractional solution, maybe. And the idea is we can do the same trick to turn like a solution which has every job split in 2 to the h parts, we can turn it to a solution that's where every job is split to the 2 to the h minus 1 parts. And that is simply, we pair the jobs together and we want to round each pair. So, for example, if you look at this pair, we want to put all of this pair on this machine or all of this pair on this machine. So, kind of we round the solution to a less fractional solution. And what happens is if you do the math, well, since we split the jobs into smaller parts, the error bound will improve. So you get like 2 to the h in the denominator because now jobs are split into small parts. So rounding from 2 to the h to 2 to the h minus 1 costs you just this. Starting with an LP solution, very fractional, we iteratively do this, and we get a nice geometric series on the errors, which we can bound by order of max Pij times square root log n, and again this is just a factor of square root log n from the optimal. So this means our natural LP relaxation with these constraints for all intervals, it has an integrality gap of square root log n. Okay, because of this rounding. Here I'm kind of I should mention that the Banaszczyk's theorem is not constructive, which means we don't actually get an approximation algorithm here because we don't know how to find these signs. But what you can still show is that the integrality gap of this LP is bounded, so at least you can approximate the optimal max flow time, like the value of the optimum, within this highly non-trivial factor. And maybe if you at some point manage to constructify Banaszczyk, then immediately you get this as an approximation guarantee.
Can you say how the prefix stuff comes in the LP? I mean, there were just a lot of constraints that come from all the release time, so I wasn't quite clear how you, how you put it all together.
Yes, we have these constraints for jobs which release between T1 and T2, and if you sort the jobs according to release time, then this subset of jobs, it corresponds to an interval in your order of jobs by release time, right? So if you bound yes, I know this has been a bit quick, but maybe
I think that's afterwards.
Good. So this gives us this nice bound, and to recap, what we show is that the integrality gap for max flow is square root log n at most. The best lower bound is a constant, and we can also do the same kind of trick if we want to minimize the sum of flow times instead of the maximum. Here you have to allow preemption and some technicalities, but we lose another log n factor, but the additional log n factor is also necessary because we kind of have a lower bound of log n in this case. But what may be interesting here is that it's widely open if Banaszczyk can be improved to a constant. If you could do this magical improvement, then our reduction, it would immediately imply tight integrality gaps up to constant for both problems. And it's even more closely connected because we can also kind of show with some restrictions the opposite direction. So prefix discrepancy is really the right way to look at these kind of problems. Okay, I'm running out of time. I just want to say as an open problem, particularly interesting is can you prove something non-trivial for two sparse vectors, because that's the only thing we need in this proof, so maybe that's much easier than the general case. Thanks.
Yeah.